Hello, everybody, and welcome to this, your final lecture here in Earth Science. Uh, Hope you've enjoyed this course. We are going to finish up today and cover now Earth in the solar system and learn a little bit about how Earth compares to the other planets, its neighbors in the solar system. So we are going to be going over all of the little things that go and float around in the solar system, not just the planets, but also different moons and smaller solar system bodies. That's the goal for today. So we'll get on with everything and take a look at this first picture up on your screen. And I want to ask you, just to start off, what's wrong with this picture? It's a depiction, of course, of the solar system, but what's wrong with it? Maybe if you take a look at it, you might guess that, well, for one thing, the planets are jumbled up a lot closer than in reality. But also, the planets are not shown at all to scale. These planets are really a lot smaller in relativity to the sun. And these last four planets, I'm trying to get my pen to work here, pardon me. These last four planets are really a lot larger than the first four planets, what are called the terrestrial planets. So these, by the way, are called the terrestrial ones. Terrestrial just means Earth-like, and these ones over here are called Jovian or gas giants. In fact, sometimes the first two are called gas giants. That's Jupiter and Saturn. The last two, Uranus and Neptune, are called the ice giants. But in any case, these are way out of proportion. So I'm actually going to show you a little bit later what it looks like if you take the planets and put them all to scale. But going on with things, the kind of outlook of what we're going to cover today are, first of all, going over each of the planets. We're going to spend some time on each planet. I'll cover quickly some of the dwarf planets, some of the moons, and also other solar system bodies. Those are things like comets, asteroids, meteors, meteorites, and then really briefly just go over quickly the origins of the solar system. I don't want to spend too much time on that since we have a lot to cover today, but you'll get the idea. So anyway, we are going to use a special unit today that we haven't ever used before. Usually we measure distances in earth science with kilometers, sometimes centimeters, sometimes microns or whatever. But we're actually going to depart from the normal metric system units, and we're going to use a different unit called an AU, an astronomical unit. 1 AU is equal to the average distance between the Earth and the Sun. Now, you might remember that Earth's rotation, its orbit, I should say, around the sun is not a perfect circle. So remember that the distance between the Earth and the sun is constantly changing. But the average distance, that's what we're going to use. It's equal to about 150 million kilometers. And so 1 AU is about 150 million kilometers, and it's the average distance from the Earth to the sun. That's how we're going to measure distances from like different planets. Basically, we're going to be comparing it to the Earth, right? So first of all, we have to go over what is a planet, right? That's the first question. What is a planet? Well, there are three parts of the definition. To be a planet, you have to, of course, orbit the sun. And that's important because, there are some moons that are almost as big as planets, right? So you think of some of the moons of Jupiter, for instance, are almost as big as Mercury. Also, you have to have sufficient mass to both reshape yourself into a sphere, but also you have to have enough mass to clear matter from the orbital zone. What does that mean? Well, if you get so large, you're going to assume roughly a spherical shape because the force of gravity has increased so much that your surface is pulled towards the center and it smooths everything out. And it's hard to maintain kind of an irregular body once the mass becomes so large and it's reshaped into a sphere. Also, when your mass becomes so large, your gravitational field increases. And therefore, you're able to suck up and clear out a lot of the debris and material that's in the orbital zone. So once your mass becomes so large, you're able to do those two things. And that's when you officially become a planet. One of the things that happened, or scientists realized, that caused Pluto to be downgraded from a planet to a dwarf planet is that Pluto, we realized, does not clear its orbital zone. So that caused that downgraded categorization to a dwarf planet from its original planet status. Here are the planets for you shown. Oh, whoops, my little light went off. Let me fix that. Boom, there we go. Okay, got a little more light now. Here are the planets, all for you, shown together. Again, Mercury, Venus, Earth, Mars, those are your terrestrial planets. Jupiter, Saturn, Uranus, Neptune, those are your Jovian planets, your gas giants. Make sure you know that for the test. I'm going to ask you on the test, straight out, what are the 8 planets in order? From the sun to the outermost reaches of the solar system. What are the 8 planets, okay? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, okay? Make sure you know them in order. Make sure also you know the difference between the terrestrial and the Jovian, okay? Terrestrial are the Earth-like planets. Jovian are the larger gas giants. They're very different in composition. We'll go over all those things later. Now, a dwarf planet. What is a dwarf planet? Like I said, it has that sufficient mass to shape itself into a sphere, but doesn't have the mass to clear out its orbital zone. So if we allowed Pluto to be a planet, we would have to include a lot of other objects also as planets to be logical and consistent. So here are all the dwarf planets in our solar system. So it's not just Pluto. There are a lot of them. And I'm not going to spend really too much time on these, but just kind of want you to know that they're out there, they exist. Now, here's a question for you. What if you orbit the sun, but you're an irregularly sized object? You don't have enough mass to shape yourself into a sphere. And you obviously don't have enough mass to clear your orbital zone. Guess what? You are a smaller solar system body. You're either an asteroid, meteoroid, or a comet. And here's kind of a complex Venn diagram type thing that you can kind of figure out, categorize what's what in the solar system. So satellites also, I just wanted to point this out. Satellites are another word for moons. So we're going to talk about moons a little bit later. Now, this is a great picture. This actually shows you, I started off showing you a depiction of the solar system. I said, what's wrong with this picture? Well, part of the problem of that picture is that everything was shown not only squished all together, well, a lot closer than it is in real life, but also way out of scale. And the reason that we do that is because if we had a to-scale picture of the sun and the other planets, you would hardly even notice the planets. The planets are so small compared to the sun. The sun is, you have to remember, the vast majority of the solar system. The sun is 99.8%, 99.9% of the mass of the solar system. So most of the solar system is just sun, okay? The little bits of inky-binky dust that go around the sun, those make up the planets. And we, of course, are much smaller. We're one of the smaller planets, right? We're one of the terrestrial planets. So you can see this is actually to scale. And I guess it's actually to you, it looks like it's up here. But to scale, these are the planets. And it's, at first you might not even notice the terrestrial planets up in the corner here, right? So I just had to circle them in red in case you missed them. There's, right, Mercury, Venus, Earth, and Mars. So, and you also notice that Earth is the biggest of the terrestrial planets. And then taking up your screen, really obvious way, are the gas giants, especially Jupiter and Saturn, right? So these are really, very conspicuous planets. Jupiter's about 394 times the size of Earth. It's much, much larger in terms of mass. All right, now here's another thing I want to show you. That's the mass, the size, I should say, of this planet's to scale. Here are the orbits of the planets around the sun to scale. And notice something about this. You see Neptune, right? Very conspicuous and noticeable. You see Uranus, you see Saturn, Jupiter. And then you're like, where are all the others? They're all here, inky-dinky, tiny, really close to the sun. It just amazes me because if you were an alien, coming to the solar system, first thing you notice, of course, is the sun. And then probably you would just not even notice these teeny little bits of dust going around the sun right there close to the center, right? So small. So we're by no means a very conspicuous large rock, going around the sun. So we're very, very easy to overlook, I would say. All right, so let's go over now just comparing terrestrial planets to Jovian planets. Okay, one of the questions I'm going to ask you on the final exam that's coming up, what's the difference between a terrestrial planet? And by the way, everyone gets this question, okay? This isn't on the question bank. This is actually on everybody's test. I'm telling you what's on the test. What's the difference between terrestrial planets and Jovian planets? Make sure you know that coming into the test. Okay, terrestrial planets, a lot of differences here. Let me go over some of them. I know this isn't necessarily on your lecture assignment, right? But it's on the final exam, so make sure you know this stuff. Terrestrial planets, composition is different. Okay, what it's made of is different. What do I mean by that? Terrestrial planets are rich in, well, you know what the Earth is made out of, right? Silicon, oxygen, magnesium, iron. Those are the things that make it up. It's rock and metal. Those are the terrestrial planets. Rocky material with iron cores. That's the normal terrestrial planet, composition. Okay, they all have rocky bodies with a metallic core. All of them have that. Mercury, Venus, Mars, Earth, right? Gas giants are different. They're mostly, of course, hydrogen. In fact, most of this solar system, like 99, well, the sun is mostly hydrogen. It's 99.8% of the solar system by mass. The biggest planet in the solar system is mostly hydrogen. Okay, so hydrogen is just a really big deal. It's by far the most abundant element in the solar system, by far. So we have hydrogen, we have some helium, we have some methane, right? Things like that. Things that are think of things that are mostly gases at normal room temperature and pressures, right? So carbon dioxide, methane, natural gas, nitrogen, things like that, ammonia. These are the kind of things that we find in the gas giants. They're made of gassy type materials, okay? One thing I want to point out here that's pretty interesting. Look at what Jupiter's made out of, and Saturn too. We have this first shell, right? Notice that there isn't like a solid surface here, right? This is like a gassy surface. You can almost think of it as like a super dense atmosphere. So we have a molecular hydrogen first shell of Jupiter. But then the second shell is something really weird. Go to the next shell. What do you see? This darker gray color. It's metallic hydrogen. What is that? Well, at the very intense pressures that prevail in the center of Jupiter, because imagine Jupiter, again, 400 times almost the mass of Earth. Immense pressures build up in the center of that planet. And the hydrogen is pressed so closely together that electrons in the hydrogen material are shared in metallic bonds. The bonds of the hydrogen shift and transform into metallic bonds. And we get a phase transition to metallic hydrogen. That means hydrogen, when you say, but doctor, hydrogen's not a metal. I know it's not a metal, but it takes on metallic properties. It becomes reflective. It becomes opaque. It's solid, right? It has high thermal and electrical conductivity. Takes on metallic characteristics, even though it's hydrogen. It's element number one. It's not a metallic element per se. Okay. One thing also that amazes me about Jupiter, Saturn, planets like that, if you look at this core, you notice it has a rocky core of rock and metal, right? If you look at this rocky core, it's this little core of Jupiter is almost the size of Earth. It's pretty amazing. So there you go. Look at the core of Jupiter and compare it. It's pretty equivalent in size to that of Earth. Okay. So let's go over, just learn about, I just kind of want to spend a little bit of time on each planet here. You get a little bit of little bit of background about each of the planets in our solar system. So first planet, of course, closest sun is Mercury, right? It's named after the messenger god Mercury, the speedy god, right? The fast god. And they call it that for a reason. Mercury is, again, he's the messenger god, so he's got to be quick on his feet. And Mercury also goes around the sun very quickly. An orbital period is only 3 months long. So that means it only takes 3 months, 3 of our months, for Mercury to go around the sun. The distance from the sun is very short, right? Only 0.38 AU. Okay, so it's 38% of the distance from the sun as we are. Another thing that's kind of interesting about Mercury, notice the rotation period, how fast this thing is spinning on its axis. It's 59 days. So that means there's really only like 2.5 days per one of their years. So in the time that it takes to spin on its axis, it's spinning very slowly. And in that time that it takes, it does only 2 rotations in the time that it takes to do a whole revolution around the sun. Now you can imagine that if you are just moving so slowly, you have a day that lasts basically equivalent of our 60 days. Imagine that during noon, it's going to be getting really, really hot on that planet, right? Because, see, we're more equilibrated here on Earth because we have, sun and night and day and night, day and night. It warms up during the day, it cools off during the night. But here you're going to have 60 days, right? 60 of our days to heat up. And that's, or I should actually say 30, to heat up, right? So that's going to be getting very hot on the surface. So you have very hot half of the planet that's facing the sun. The other half of it gets very cold, okay? Huge diurnal temperature variations. 800 degrees Fahrenheit versus negative 280 degrees Fahrenheit at night. So it's, not a place you want to live, right? Has a very weak magnetic field. Remember how important that magnetic field is. That magnetic field is what helps us sustain life here on planet Earth. It protects us from solar winds. Also protects the atmosphere from being blown away by solar winds. So you can imagine that Mercury has no atmosphere, none. Okay, it's too small, has not enough mass to keep the atmosphere tamped down. Remember that gravity is what holds our atmosphere in place. If you don't have sufficient gravity, you're not going to have an atmosphere. Furthermore, if you don't have a magnetic field, that protects the atmosphere from being blown away by the solar winds. If you don't have a magnetic field, you're not going to have an atmosphere. So there's no atmosphere here on Mercury. Okay, no moons. Density of very equivalent to Earth. We have a density of 5.5. Mercury has one of 5.43. So you'll notice that even though it has a molten outer core, it has no magnetic field. Why? Because it's not spinning fast enough. So isn't that amazing? I always put all these things together and I'm just amazed because there's so many things that have to be just right in order to maintain life and have a habitable planet, right? If you're not spinning fast enough, that creates a lot of problems in terms of habitability, okay? So you have to be at the right distance from the sun. You have to be the right size. You have to be spinning. You have to have a regular orbit, not have extreme eccentricity in the orbit. You have to have a stable orbit. So many things have to be just right. We call it the Goldilocks zone for habitability. Be just right to maintain habitability on a planet. So there's a picture of Mercury. And if I didn't tell you that this is Mercury, I bet a lot of you would just say, oh, maybe that's the moon. It looks a little funny, but I don't know. Is it the moon? But it looks a lot like the moon, right? And of course it does. It's kind of similar in size. It's pretty close to the same size, and so similar composition. It's like a rocky body, right? So moving on to Venus, and I guess also like the moon, there's no really atmosphere to speak of. So of course it looks similar. All right, Venus. Venus is our sister planet. It's the planet that probably we're closest to in terms of our properties. You know, a lot of people think, oh, Mars, that Mars is our... No, Venus is really the one that's closest to us. Venus has a similar size to Earth. It's about 82% of our mass. It has a pretty close density to Earth, 5.25 versus 5.5 for Earth. No moons on Venus. But there are some things that are also Venus, by the way, contrary to popular belief, Venus is actually the planet that gets closest to us. It's 0.72 AU away from, so 72% of our distance from the sun. So it's the one that gets closest to us at any given time. Not any given time, but at certain times, actually. All right, so the orbital period here is 7 months. It goes around the sun in 7 months, 7 of our months, of course. But notice again the rotation period, 243 days. So it's in a really extreme position where it's really only, well, what is 243 days, huh? Let's see, 243 days divided by 12, 243 days divided by 12, that equals 20.2, 243. I'm doing the wrong thing. 243 divided by, let's say, 30 days in a month, right? So that's about 8 months, okay? So that means that, yeah, this is going a lot, only having basically less than a day in its year. You know, you see what I mean? So it's only spinning around once on its axis of rotation in the course of a year. So really, really slow. Also notice here something else. The rotation period is negative. Do y'all see that? So the rotation period is negative here on Venus. What does that mean? Well, I always like to joke around that Venus got smacked when it was a kid, and that's why it's all messed up and funny. And what do I mean by that? Well, we think that there was actually a massive impact on Venus during its early history, and that caused it actually to, boom, spin the wrong direction on its axis. Because everything in the solar system, by the way, in case you didn't know this, spins basically counterclockwise. So if you're looking down at Earth from the North Pole, right, it's spinning counterclockwise. So Venus, though, is a freak. It goes the opposite direction, spinning the opposite direction on its axis than it should, and also very slowly. Okay, so you can imagine that because of this slow spin, there's no magnetic field really to speak of. But because of its great size, it does have an atmosphere. And notice something interesting here. The atmosphere is actually 100 times thicker than we have here on Earth. So if you were on the surface of Venus, you'd just be crushed by this atmosphere. You'd have extreme atmospheric density and air pressure pushing down at you. Atmosphere is mostly CO2. Okay, it's like 95% CO2. A super greenhouse gas effect, which traps heat and makes it basically uninhabitable. It's hot enough there to melt lead. You don't get this supreme temperature diurnal effect that you get on Mercury because this greenhouse gas effect is so strong it basically equilibrates the temperature, makes the temperatures basically equal through day and night. However, you do get just extreme temperatures, hot enough to melt lead easily, 600 degrees Fahrenheit almost all the time. So it's very, very hot, uninhabitable place. No magnetic field, as I said. Notice that I just kind of want to point something out to you about Venus and Mercury. Do you notice that when you look at pictures of Venus and Mercury, lots of craters? Do you ever notice that? The moon, too, a lot of craters, but you don't see that on Earth. You might think, well, Mercury has no atmosphere. Maybe it gets pelted with a lot of small things, and that's true. But Venus has a really thick atmosphere, but it still gets craters on it. Why does it have so many craters? It's because the role of water. Earth gets pelted with a lot of stuff too, but the craters are eroded away very quickly because water's constantly falling on the surface and weathering the craters away and filling them in with sediment and eroding the rim, etc., etc. So they disappear after not too long. But that doesn't happen on Venus because there's no water, right? We actually do have some pictures, surprisingly, from the surface of Venus, and these are thanks to the Soviets in the 70s and 80s. Actually sent missions to land on Venus, and they were successful 2 times. They brought back pictures, or I should say sent back pictures, before the probe was disintegrated due to the intense heat on the surface there. You could imagine that a probe is not going to last very long because of the temperature is so high. And you could see basically a hellscape, a horrible, horrible hellscape. The rock that you're seeing is probably basalt, and the sulfuric gases rain down like a sulfuric acid on the surface, almost like rain. So it's a horrible, horrible place, not somewhere you'd want to go, but it is cool to have pictures from the surface of Venus. A planet that we know a lot about, Mars, of course, is one that we've landed a lot of rovers on. I know Elon Musk wants to make this like build like a biome there and all sorts of things, and has these ideas about terraforming Mars, etc., which I don't really think is possible. But aside from that fact, distance from the sun for Mars is 1.5 AU. We know a lot about Mars because we've sent so many missions there. We have so much information about it now. Has an orbital period that's 1 year and 11 months, so it takes about 2 of our years for it to go around. Has a rotation period very similar to Earth. It takes about 1 day. So if you did live there, if we ever had Martians, humans living there, they would have days similar to Earth. But notice it only has a mass of about 11% of that of Earth. So much, much smaller planet than Earth is. Again, and by the way, I didn't mention this, but Mercury is even smaller, right? Mercury is only about 5% of Earth's mass. So it's a very small planet. Really, as I said, not too much bigger than our moon, really. Density is pretty low, about 4 grams per cubic centimeter compared to our 5.5. We are the densest planet. Earth is the densest planet, by the way, of the whole solar system. It has 2 moons, which are fairly small, called Phobos and Deimos, which mean fear and hate. Any idea? Just a little trivia quiz for you. Why Phobos and Deimos? Why fear and hate? Why give them such a horrible name? What do y'all think? If you're guessing, it's because of Mars is of course, the god of war. So that's why fear and hate always go along with war. So that's why the moons are called such. The atmosphere is very, very thin. Thin CO2 atmosphere, mostly, again, carbon dioxide, about 95% carbon dioxide. Because the atmosphere is so thin, what's kind of interesting, I was reading a little bit about it. If you're at the equator on a nice day in Mars, and by the way, Mars also has seasons like Earth because it's tilted about similar to Earth, about 25 degrees on its axis. If you're, though, at the equator on a nice day, your feet might be 75 degrees, maybe 70 degrees Fahrenheit. Pretty nice, right? But your head would be almost freezing because there's so thin atmosphere, so little atmosphere, that as soon as you get a little bit above the ground, the temperature drops. So you have like a super high lapse rate, basically, if that makes sense. So anyway, your head would be really cold, but your feet would be nice and warm. Something to think about. But generally speaking, the temperatures there are very, very cold. Here are some beautiful pictures from Mars. And, if you didn't know better, you might think, maybe it's Earth, right? You might think this is a desert or something. So these are you see mountains, deserts. Most of the rock here is basalt. Has also sand dunes. Okay, does have winds made of CO2. Here are the ice caps, and this is pretty interesting. I wanted to talk about this. When I first did this lecture, actually this is now outdated. When I first did this lecture, these were thought of. Back when I started doing this in about 2018 or 2000, no, earlier than that, these were thought to be just basically pure CO2, and that actually has changed over the years, right? So actually we see that these polar ice caps have a thin layer of CO2 basically dry ice on the surface, but underneath there is H2O ice, ice made of H2O, made of water. So there is water on Mars. I shouldn't say water, but ice, H2O ice on Mars. So with the polar ice caps do have some H2O there. Also, there is some H2O, we think, possibly subsurface. Almost like, you can almost think of like groundwater, or maybe a better example would be something like almost like permafrost, something like that. Not water, liquid water, but ice. Okay, so there is H2O on Mars. I did also want to talk about Olympus Mons, which is the largest volcano in the solar system. This is 72,000 feet high. That's 3 times the height of Mount Everest, or not quite 3 times, but maybe 2.5 times the height of Mount Everest. And this picture that you're seeing right here of this, I guess what you're looking at is up there, or up there, I can't remember. But anyway, it's the size of France, what you're looking at. So it's a huge, huge volcano of basaltic lava. This used to be an active planet, used to have a lot of plate tectonics on it. We think that it used to have abundant free-flowing water. We have a lot of evidence for that there was abundant free-floating water at some point in Mars's history. However, that water has frozen. So we think that, Earth, maybe Mars was more Earth-like earlier in its history. Maybe the temperature was nicer, better. But now it has all frozen. All the H2O is frozen and gone. So these are pictures of basically sedimentary, what look like, if you look at these, look like a riverbed, right? It looks like pebbles, rounded pebbles. We actually see rocks, which you might identify as a conglomerate rock, right? So these are sedimentary rocks that are deposited by water. You can see these kind of pebbles, obviously water. It looks like as if water was shaping them and eroding them. Also, we can find a lot of chemical evidence for chemical weathering, hydrolysis with water. So that shows also that water was definitely a major factor in shaping the morphology of Mars' surface early in its history. But those things have seemed to have passed away now. The climate has changed there, it's gotten colder, and now we don't have liquid water at the surface anymore, as we might have had far in the past. Jupiter is now, we're going to start the Jovian planets. Now notice suddenly we're going to jump way out. We go from 1.5 AU, Mars, we jump way out there, and we go all the way out to 5 AU, 5.2 AU. So we suddenly get a lot further out. And we have Jupiter, the largest planet in the solar system, 394 times the size of Earth. Or sorry, I'm mistaken, 318 times the size of Earth. We can almost think of it as a failed star. Maybe something that was competing with our sun to attract hydrogen and mass and growing through accretion, gravitational collapse. But ultimately the sun won out and Jupiter became a planet. So the orbital period is 12 years. That means it takes 12 years for Jupiter to go around the sun. But it only takes 9 hours for it to rotate on its axis. So it's rotating super fast. And because of that rotation, and also because of the metallic hydrogen, Jupiter generates a very strong magnetic field, All right, so density is only 1.3. That's because of all the gases there. Okay, gases have a lower density than rocks and metal, obviously. The moons are, I put 10 plus here because it's not just, there may be 10 pretty large ones, but there are many, many objects that are captured in Jupiter's, sizable gravitational field. Atmosphere is, of course, it's kind of a question of where does its atmosphere begin, right? Because the first top layer is mostly molecular hydrogen, right? So you can almost think of that top layer above the metallic hydrogen as being atmosphere, right? So it has a atmosphere, heavy one, of hydrogen, helium, ammonia, etc., etc. Okay, it has 4 big moons. These are called the Galilean moons. You can actually see these with a not very good telescope. If you point it at Jupiter, you can usually see these 4 big moons. You have Callisto, Ganymede, Europa, and Io. by the way, in case you know anything about Greek mythology or Roman mythology, these are all the boyfriends and girlfriends of Jupiter, okay, king of the gods, right, Zeus. So all of these are different moons of the big moons of Jupiter. And some of these are, again, about the size of planets, like the size of Mercury, right? They're very big. And here they are compared to Earth, right? Ganymede especially, you can see is, it's getting there. It's almost Earth size. Definitely almost maybe even Mars size, something like that. And you can see some of these are definitely bigger than our moon. Now, Europa of these is one of the most interesting to us because we know that there is liquid water on Europa. And not only does it have liquid water H2O geysers that are erupting on the surface, but the gravitational field that we can sense remotely from satellites tell us that it's kind of consistent with there being a liquid water layer. So it'd be really interesting to explore that liquid water. There's a thin layer of ice, and we think below that there's a liquid water layer. So I shouldn't say a thin layer, but there's a layer of ice, H2O ice. And if we could get below that, we think that there might be a liquid water layer, and who knows, there could be life there. So NASA is very involved in trying to develop a probe that can drill into the ice, deposit some kind of a rover or ROV, a remotely operated vehicle that explore those oceans. Next one up is Saturn. Now, of course, Saturn's famous for the rings. It has a distance of 9.5 AU. So again, you have to go out another 5 AU past Jupiter, almost another 5 AU to get to Saturn. The orbital period is about 29 and a half years. Wow. And rotation period, again, rotating very fast, 11 hours. And you can see it's rotating really fast. It has a lot of centrifugal force in it. So you can imagine that's going to pull a lot of that material out to the outside. And that's what helps it to maintain its famous rings, which are made of dust and ice. And that's kind of material that's spinning so fast it's hard for it to conglomerate together and form into the planet. Okay, so now the mass is almost 100 times that of Earth, but its density is very low. So low that they kind of say this, it doesn't really make any sense, but it could float in water if you were to put it in water. So it's really just, it kind of doesn't make any sense because if you had a bathtub big enough to put Saturn in, it would form itself into its own planet, whatever. But my point is, it has a very low density, less than that of water. Has 13 plus moons. Why I say plus? Because there's so many objects around Saturn. It's not just 13. There are a lot of things. Some of them very small, right? But they are orbiting around Saturn. Okay. Atmosphere is H2O and helium. So hydrogen and helium. Okay. Rings are composed of dust and rocks orbiting the planet. Many small moons also orbit Saturn. Here are some of the big ones. Tethys, Rhea, Titan is really the largest one. So you have the rings, and then you start to get these moons. Enceladus is also an important moon because it's yet again a moon where we think there might be liquid water, very similar to Europa. Titan is the largest of the moons there, but you can see these are all the moons of Saturn. There's just a ton of them, right? A ton of them. Some of them are very small, though, only 50 kilometers, right? It's not very big at all. Okay, one of the largest moons, Titan. We actually tried to send a a rover there, a probe there, but the mission failed. It landed on the surface of Titan, and we didn't realize how kind of slushy the surface is. It's mostly made of like methane and lighter elements, ices, and we thought it was more solid than it is, and actually sunk and got trapped and sunk into this kind of icy methane slush. Kind of sounds weird, right? But that's what happened. So it was a failed mission, mostly made of hydrocarbons like methane. So anyway, the surface is negative 180 degrees Celsius, low enough to maintain these things like methane as an ice, as a solid. Titan is actually larger in volume than Mercury. Not in mass, but in volume. Okay. Going on to the ice giants, the last two planets. We have Uranus and then Neptune. Okay, Neptune's the last one. Okay, these are 19 AU out there, and then 30 AU for Neptune. And look at these things go around. Uranus goes around 84 years, Neptune in 164 years. Wow. So you will not experience Neptune making a full revolution around the sun. If you lived on Neptune, you wouldn't live at all. But even if you could live there, you would never experience a full year on Neptune, right? So another thing that's kind of interesting about Uranus is that it actually, there's a picture of it relative to the Earth, and has these 6 large moons. But kind of the most interesting thing about it is it has an extreme rotational tilt, where it's almost tilted 90 degrees on its rotational axis is almost in line and parallel with the with its ecliptic plane. So it has that real extreme axis. So it's amazing, because basically a winter here would last half of the orbital period, so 40 years, right? And then a summer would be 40 years long. Of course, you get very little light and heat from the sun out there, so it's a very, very cold place, of course. These ice giants are mostly made of, again, you guessed it, hydrogen, helium, ammonia, things like that. Light, gaseous type elements. Okay, so there you go. These are the orbital periods of all the 8 planets. I like this little animation. And you can see that's Neptune going around on the outmost. You can see Saturn and Jupiter and all these. It's funny because the terrestrial planets are going around so fast you can't even see them. They're just whizzing really fast. You can't even see them going. So anyway, that's how they look in real life if you were to actually look at the animation of them all spinning together. So anyway, I just wanted to, again, encourage you all to go out, look at the night sky on nice clear nights. There's lots of really cool apps you can use, and you can actually just point the phone at a certain part of the night sky, and it'll tell you what part of the sky you're looking at. So pretty interesting. So I encourage you all to do that. Get out there and look at the stars and familiarize yourself with the planets. Usually Mercury, you can't usually see it very well, sometimes early in the morning. Venus, though, is really prominent, especially early in the morning. We often call Venus the morning star. Jupiter is very, very prominent. Usually when you go out at nighttime, you see the bright star. It's probably Jupiter. Very, very likely Jupiter, if Jupiter happens to be out during that time of year. And you can even with some good binoculars, you can see the Galilean moons of Jupiter. So go out there and take a look and familiarize yourself with the night sky. It's a lot of fun. So going on to smaller solar system bodies, comets. Comets are small, solid bodies of frozen. Basically, I think of them as dirty ice balls, right? Dirty slush balls, containing H2O, CO2, NH4, that's ammonia, and CH4, that's methane. Okay, comets do orbit the sun, but a lot of them have very extreme distances from the sun. They're going around maybe every hundreds of years, right? And they originate maybe they might be 30 AU out there, way beyond Neptune, all the way out. I mean, we still have material that's 1 light year away that's still orbiting the sun. So it's really amazing. As comets pass close to the sun, some of these have very highly elliptical orbits, so they spend most of their time, maybe they're far away, but then they get close to the sun for part of their orbit. When they approach the sun, they start to volatilize and give off ionizing energy that we see as a tail. And what's kind of interesting here, I just want to point this out. When you see this tail, a lot of people think like, oh, it's moving in this direction, right? The comet's moving in that direction. It's moving like that, and the tail you see is all the stuff streaming out behind it. That's not true at all, actually. What the tail that you actually see is being blown off by solar wind. So the sun is over here. the sun is actually, that arrow pointing, it was actually pointing to the sun. That comet could be moving like that, but the tail you see is just from the solar wind. It's pointing you, showing you the direction to the sun, basically. You could also have, we also have asteroids, right? So asteroids go around the sun, but they are not large enough to shape themselves into a spherical shape. Okay, we of course have the very famous asteroid belt that goes around the sun, and it's between Mars and Jupiter. And a lot of people think that, a lot of scientists think, I should say, that if it wasn't for Jupiter's great mass, this asteroid belt would have conglomerated together, accreted together, and become another terrestrial planet. But because of the great mass of Jupiter, it interrupted that accretion process, so it never accreted together like the other planets did. Meteorites, meteors, and meteoroids. If you're just floating, a little rock floating in outer space, we call you a meteoroid. If you strike Earth, or I should say strike our atmosphere, and you see a streak across the sky, we call that a meteor. And if that little piece actually, boom, strikes the Earth, you have a meteorite. So meteorites, of course, can make these very dramatic, when they strike the Earth, you get these very dramatic things lighting up the night sky. And if you ever see shooting stars are just meteoroids, meteors, right, striking Earth's atmosphere. And of course, they're going so fast. You have to remember, some of these things are going like 17,000, 10,000, 20,000 miles per hour. Going super fast. It's way faster than a bullet. Way, 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 way more energy than a bullet. So when these things strike the atmosphere of Earth, it's just like hitting a brick wall. So they start to vaporize, they start to burn up. They're burning and vaporizing and reacting with the oxygen in the atmosphere. And that's what creates the big fire that you see. This is a video I wanted to show. This was a meteor strike that happened in Michigan when I used to live there. So it was a really big deal at the time. It was caught on tape.
Very strange event took place in the Metro Detroit area around 8:08 p.m. local time in Detroit. A massive bolide exploded over Detroit with a loud boom that shook the ground and windows and doors and everything else. Here's that video, guys. If we have any more information,
so there's a dash cam image
exploding over Detroit,
and it's amazing.
We'll make another video and keep you updated
because it just lights up. You'll see it lights up the whole sky.
Coming in at a steep angle.
Looks like it's daytime for like 1 second, right? So much energy coming out of there. Here's the snowy Michigan. There's the bolide coming down. So pretty amazing. So that was right there at University of Michigan around this time when it struck. Pretty amazing stuff. So these are what meteorites look like. They contain just invaluable information about early Earth history, early solar nebula. These were basically samples. A lot of these like stony carbonaceous chondrites, like this one you see here, are pretty representative samples of the early solar nebula and what the early solar nebula might have looked like and might have been like, and what chemically it consisted of, right? These amazing iron meteorites, we have quite a few in our collection here at Del Mar College. If you ever get the privilege of taking a face-to-face geology class, actually are samples, believe it or not. These are samples of the cores of planetesimals and planets that used to exist but blew up in the early chaotic, violent, history of our solar system. So these were the cores of those planets that exploded, and the metal shrapnel was spread all throughout the solar system. Okay. Speaking of the early solar nebula, I do want to just finish up here with an explanation of how the solar system formed. And I'll begin just by saying that kind of the first step that happened was very early, before our solar system actually began to form. We think that there was probably a supernova close by, in close proximity to in the galaxy, to where our solar system currently is. And we think that because in our solar system we have elements that are heavier than iron. And what I mean by that, like we have things like gold and uranium and lead and copper and stuff like that. You might be saying, well, so what? Well, so what is that the only way to make those kinds of elements, I know this sounds crazy, but it's true, but the only way to make those kinds of elements are actually in supernova. So the fact that we have those elements in our solar system shows us that probably there was a supernova very close by, very close to when we started out. So we're what's called a second generation star. That means that before our star formed, there was another star that began, lived out its life, collapsed, and became a supernova, and then jump-started the formation of our solar system. Our solar system started off as a nebula. That just means, nebula is just Latin for cloud. It's a cloud of dust and gas, mostly hydrogen. And the supernova, we think, triggered a gravitational collapse. As it collapsed, it started to spin faster and faster. That caused the cloud not only to collapse, but to start to thin out into a nebular disk, a accretionary disk. Over time, that disk became stable. It began to accrete into the planets. And once the pressure built up so much in the center because of the intense amount of material that had accreted together in the center, that kick-started and ignited the sun and initiated hydrogen fusion in the sun. And that hydrogen fusion is what continues today and provides all the energy for our solar system. So that's all for you today. There's a real quick overview of how our solar system began. I hope you enjoyed the class. I hope that you learned something that you value, and I hope that you go on to do great things at Del Mar College and beyond. So thank you for listening, and I just want to say that make sure that you study hard for the final exam. I have a lot of final exam review videos up there and study guide up there, so start to study hard now and start studying early, getting ready for your final exam. Please let me know if you have any questions and if there's anything I can do to help you better prepare for the exam, because of course I want you to succeed and be successful on that exam and in the class. So good luck, and I will see you next time.